Hi there, we're going to derive the equation of motions of a double pendulum. Now, when we think about this point here as being the fulcrum, so that's a fixed point. Now, that's one of the pendulums there. It's length L1 and it's got a mass at the end of it, M1. Now, the other pendulum is connected to it and it's got length L2 and its mass at the end of the pendulum is M2. Now, we look at the angles that the pendulum makes with the this axis here. Okay, so that's the axis there, the y-axis, and we're looking at the angle it makes with that axis. Now that angle there, we define that as theta 1, and then we look at the angle that this pendulum here makes with that axis, and we define that as theta 2. So we're looking to find what the motion of this system is. So we can split it into looking at the motion of this pendulum here, because this one will sweep round in a circle. So that would be an inner circle. And we look at it in terms of how this mass here will sweep round in a circle as well. And that would be an outer circle. So we can in turn separate these movements into an X movement and a Y movement. Okay, so the first one we're going to look at is we'll look at the internal pendulum. So we're going to look at the length x1. So x1 is from here to the mass here. Okay, so that distance there, well, that can be written quite simply as x1 equals, so it's going to be L1 sine of theta 1. So L1 sine theta 1. So we'll just give these numbers just to keep track of them. Now, the distance x2, which is the distance from this point here for this pendulum, okay, so the full x distance for this pendulum here is going to be x2 is going to be, well, it's going to be the x1 distance. Okay, so it's going to be the x1 distance plus this extra distance here. Okay, now that distance there is just going to be our L2 and sine of this theta 2. So it's just going to be L2 sine of theta 2. Okay, so we'll call that number 2. And we're also interested in the y distances. Okay, so we can see that y1 is equal to, if we write it down, y1 is going to be equal to L1 times the cos of this angle theta 1. So it's L1 cos of theta 1, and we can write, we'll call that 3. Okay, now we can also look at this distance here, which is the full distance y2. So y2 is the y1 plus this extra distance here, which is this height here. Okay, so we can say that y2 is going to equal y1 plus, well, that extra distance there is going to be the L2, but it's going to be L2 times the cos of this angle theta 2. So it's going to be L2 cos of theta 2. So we'll call that equation number 4. Okay, so these are reasonably straightforward, these equations here. Now, what we're interested in is the movement of these. Okay, so when we say the movement, we're interested in the velocity. Okay, so we're interested in the velocity of this point here and also this point here. Okay, so now what we'll do is we'll split the velocities again into the component parts. So there's this end of the pendulum, the point M1, has a velocity in the x direction and a velocity in the y direction, and M2 has a velocity in the x direction and in the y direction. Okay, so we can say, let's look at the x component of the velocity of m1. So so I'll write that down. So it's x component of the velocity, I'll just say v, okay, v of mass m1. Okay, so we've got m1 there, and it's just the x component of this velocity, this mass m1. Okay, so what we're interested in is the x component of velocity. So to get the velocity, we differentiate the position with respect to time. There's nothing new in that. So velocity is rate of change of position with respect to time. But of course, if you note up here, we note that this distance x is a function of theta. Okay, so that means that when we look at dx by dt, in order to get dx by dt, we've got to use the chain rule, and we've got to look at the rate of change of dx with respect to d theta, okay, times the rate of change of d theta by dt. Now it's important that you understand where that comes from. We are looking at the rate of change of x with respect to time, but we know that x is a function of theta, so we have to look at x with the rate of change of x with respect to theta times theta with respect to t. So it's just the chain rule for differentiation. So we can write down then, now we'll replace this dx by dt with x dot. Okay, so we say x dot is going to equal, well, that's going to be equal to dx by d theta. So let's have a look and see. So the first point here is we're looking at dx1, okay, so this here, so we're going to differentiate that with respect to theta. So the value L1 is just a constant, and we're differentiating that with respect to theta, so we're going to have our L1 remains as it is, and this is going to be differentiate sine theta becomes cos theta, so that's cos theta 1, okay, and we're multiplying the whole lot, so that's this part here, and we're multiplying the whole lot by d theta by dt. Okay, so d theta by t is just going to be our theta dot. Okay, so we can call that 5, call that equation 5. Now we can then write that x2 dot is going to equal, well, it's just going to be our x1 dot, okay, so it's going to be our x1 dot, which is our L1 cos theta 1 times theta dot, okay, times theta dot, plus, and we've got our L2 sine theta dot, so we're differentiating this one as well, okay, so we're differentiating that sine theta again, so we're going to have just our L2 as the constant, and we're differentiating with respect to dx by d theta, so we're differentiating that with respect to theta, so that's just going to be our cos theta 2 dot times the d theta by dt, d theta by dt, so I won't write it as d theta by dt, I'll write it as theta dot, okay, keeps it simpler, okay, so that's just going to be our theta dot, okay, so I've got to get rid of that little dot up there as well. Don't want that, it's just confusing things, that little dot there. Okay, so that there, we'll call that equation number 6. So don't get lost in this, all we've found there is the rate of change of the x coordinate, okay, of the first mass, okay, with respect to time. So we're looking at this here, and we're looking at the rate of change of this distance here, x, with respect to time. Okay, so that is this equation here. So now we can go and we can look at y1 dot, and we go through the same process. So y1 dot, well, it's going to be our L1 is a constant, so L1 is a constant, and if we differentiate cos, we get minus sine, so it's minus sine theta 1 times theta dot, and that's theta 1 dot, I should say, with all of these, theta 1 dot, theta 2, that's theta, so it's going to be theta 2 dot, okay, and we can also write then that our y2 dot is going to equal, well, it's a minus L1 sine theta 1 times theta 1 dot, and we're going to differentiate the other part of this as L2 cos theta 2 dot, so it's going to be cos theta 2 becomes minus sine, so it's going to be minus L2 is the constant, and we're going to have sine theta 2, and we've got the rest of the differentiation, the d theta by dt, which is theta 2 dot. Okay, so the chain rule I was talking about, so we've got the rest of the chain rule there. Okay, so that there then is, we can maybe call that 6, we'll call that 7, just so we can keep track of them all, and we could call that one number 8. Okay, so now again, let's not get lost here. All we're looking at the rate of change of the values here, are x1, so we're looking at a rate of change over, and that's going to be an x1. Okay, that's theta 1. You can make sure we get all the numbers in there here that we need. So we've found the velocity of this point here, the end of this pendulum in the x direction, so that's that there, and we've found the velocity of the end of this point, this pendulum here, in the x direction, and also the y direction of velocity of this point and the y direction of velocity of that point. Okay, so that's what these 4 equations here, 5, 6, 7 and 8 are given us. Now we're going to use the Lagrangian in order to work out the equations of motion. So we're interested in finding the total kinetic energy. So we're interested, we call the kinetic energy is used called T. So kinetic energy is written as a half mv squared. Okay, so you could say then it's going to be a half m. Now the velocity is a velocity in an x direction and a y direction. Okay, so it's a two-dimensional velocity. So we could say the velocity could go as x1 dot. Okay, so the rate of change of position in the x direction with respect to time, plus y1 dot, which is the rate of change of position at squared as well, obviously squared with respect to time. So this is squared value here. Okay, so that there would be the kinetic energy for the mass m1 Now we've also got to add in the kinetic energy for the mass m2, so you're going to have half m, I'll put that 1, and that's going to be 2, and it's going to be x1 dot squared plus x2 dot squared. Okay, now what we have to do is we have to substitute these 5, 6, 7 and 8 into this equation here in order to get the total kinetic energy. So if you bear with us here, we'll put these in, so we can say T is going to equal a half m1 times, now we're going to have, just repeating these ones, so it's x1 dot squared, so that's x1, it's that one there, okay, squared. So if you go to put all these in, I'll just write them in here and you can always check them yourself. So L1 squared, and we're going to have our theta 1 squared, okay, so that's the theta 1 dot, theta 1 dot squared, theta 1 dot squared times cos squared theta 1, okay, and it's going to be minus to get the putting the x and y's in the same spot, so we're going to get our half mv, so it's a vy, there's a y point there, so it's this one here, so we're going to have minus L1 squared, okay, times theta 1 dot squared, theta 1 dot squared from here, and we're going to have our sine squared theta 1. Okay, so that there is the first part of it here. Now the second part of it is going to be plus a half m2, and we're going to have our next part of it. So we're looking at the xy, so we'll look at xy for the second part here. The xy for the second part here is this here, okay, so now we're going to have our this here squared and that squared, so it's going to have our L1 theta 1 dot times cos theta 1, okay, plus, now come down and onto the next line, this is where it gets quite long and involved, so I'll put in plus the L2 theta 2 dot times cos theta 2. Now it's that whole thing there squared, okay, so it's that whole thing there squared, right, and now we've got to do the same one for this one here, and this whole thing here is going to be squared, so it's going to be plus the minus L1 theta 1 dot sine theta 1 minus L2 theta 2 sine theta 2. That's that whole thing squared. Okay, so it's just that thing. It was that thing. Get my. So it's that part there squared plus that part there squared. Okay, so that there is the kinetic energy. So we can gather together some like terms and we can simplify it there, use a little trig identity to get it simplified. So we can write that whole thing out. Now I'll expand the whole thing out, and again you can check this yourselves by pausing it and just having a look. So we can then say that T is going to equal a half m1 times, well, it's going to be L1 squared theta 1 dot squared cos squared theta 1, okay, the first part here, minus L1 squared theta 1 squared sine squared theta 1. Okay, so that's just the first part here. Now we've got to do the squares for this and the squares for that one there, so we're going to end up with a half m2. Now this is going to be times, well, the first part of the first one here is this squared, so it's going to be the L1 squared theta 1 dot squared cos squared theta 1 plus, now it's going to be 2 times the L1 theta 1 dot cos theta 1 L2 theta 2 dot cos theta 2, and then the last part of that one is plus L2 squared theta 2 dot squared cos squared theta 2. Okay, now I'll bracket that because that's the first part of this, so it's that one squared out. Now we've got to square out this one here as well, so you're going to end up with our next part of that, which is plus, I'll put it on a new bracket, so that's that one, that one, that one, so we're going to have L1 squared theta 1 dot squared sine squared theta 1 minus 2 L1 theta 1 dot sine theta 1 L2 theta 2 dot sine theta 2, and the last part of that is plus L2 squared theta 2 dot squared sine squared theta 2. Now that you can see it's all a bit long and involved, but we can simplify that a little bit, because we can write that as, and you can convince yourself of this, but that can be written as a half m1 plus m2. So what we're really doing, if we can circle some of these round about so you can see, you have this term here. Maybe I can, if it just adds a bit of confusion in. This term here, okay, and you have that term there, and you can add on, that's L1, 2, and we can add on the same thing here in this term here, L1, 2 squared theta, this one here, so that term and that term there. Okay, so if these two terms, that one and that one, we can add those together, okay, and we're going to end up with sine squared plus cos squared, which will actually just give us a value of 1. Okay, so then we can also look at another two terms, say this term here, okay, along with which one it will be? It'll be the next term along with the M2, which is L1 squared, L2 squared, L1 squared. Okay, so it'll be this term here along with this term here, and we've got our sine squared plus cos squared, which again would give us our 1. Okay, but it would be plus 1, and that one, those two here, would give us minus 1. So the plus 1 in these, the minus 1 in these two here, so I'll just bracket that. Minus 1 in this one, and in this one. Okay, then these four terms will just cancel out. Okay, and we'll end it up with, in the end, just a half m1 plus m2, and it would be L1 squared theta 1 squared plus a half m2 L2 squared theta 2 dot squared plus, and we would have m2 L1 L2 theta 1 dot theta 2 dot, and we'll have also the end of that will be cos of theta 1 minus theta 2. Now we'll give that equation number, let's see, 9. We'll call that equation number 9. You can see it's just really kind of algebra, a lot of algebra. Okay, so equation number 9, now we got that cos, remember the cos, the double angle formula, so if you have cos of theta 1 minus theta 2 equals cos theta 1 cos theta 1 cos theta 2 minus sine theta 1 sine theta 2, and we used this identity here because we had a sine here, so it was a minus sine, and there was a plus cos. Okay, so we're able to take this one here and this one here and connect it together to write it in that form there. Okay, cos theta 1 minus theta 2. Okay, so that there is the kinetic energy, okay, of the double pendulum. Again, very easy to make a mistake with your dots all the way through. Okay, so you can just check through and see whether you see any errors in that. Okay, so now the potential energy, so we're interested in the value of our potential energy, so we'll call that U. So we're looking at U, and we know that U equals, well, potential energy is dependent on the position. Okay, so it's going to be mass 1 times the gravity times the function of this mass with respect to the y coordinates. So we'll just call it y1. So it's really y of x, so it's the position, the y position of that pendulum. Okay, and if we add in the same for the second mass, so you're going to have m2 g times the position with respect to y of the y2. Okay, so that's reasonably straightforward. So then we can write that u equals, well, the coordinate system, will call it negative g, so it's negative g, and you're going to have m1 y1 plus m2 y2. So that's going to equal, now we just put our values in for these as well, so it's going to equal minus g, then it will be our values y1, y1 is L1 cos theta 1, so you have m1 L1 cos theta 1 plus a value m2, and the y2 is L1 cos theta 1 plus L2 cos theta 2. Okay, so these, we're just getting these here from the y1 and y2 here, this one here, and this one, oh sorry, first one's here, so it's this one here, right first, right up the very, very top, this one here, and this one here. Okay, so that's us got the potential energy. Now we can rewrite that out as U equals minus G, and we're going to have M1 L1 cos theta 1 plus M2 L1 cos theta 1 plus M2 L2 cos theta 2, and then we can finally rewrite that as U equals minus G, and we'll have gathered in like terms M1 plus M2, okay, M1 plus M2, and we have L1 cos theta 1 plus the value M2 L2 cos theta 2. Okay, so that there is the equation for the potential energy of a double pendulum. Okay, so we can call that one, that was number 9, we'll call that number 10. Number 10. Okay, now what we're going to do is look at the Lagrangian. So Lagrangian is equal to the total kinetic energy minus the total potential energy. Okay, so when we write that out, we're just going to have number 9 minus number 10, so that will just be Lagrangian L is going to equal a half M1 plus M2 L1 squared theta 1 dot squared plus a half M2 L2 squared theta 2 dot squared plus M2 L1 L2 theta 1 dot theta 2 dot cos of theta 1 minus theta 2, and then the potential energy is plus G M1 plus M2 L1 cos theta 1 plus G M2 L2 cos of theta 2. Okay, so that there is the Lagrangian for the system. Put a bracket around that one there. Let's see, and we can call that number 11. Okay, and now we worked out the Lagrangian, we can now use the calculus of variations. So we know that the Euler-Lagrange can be written as d by dt of, now the general one we can write it as partial L by partial Q I dot, okay, minus partial L by partial Q I equals 0. Now, if you're wondering where that comes from, I've got a playlist there on the calculus of variations, and that gets derived in that, so you can look at that full derivation in the calculus of variation section. But just quickly speaking, that shows you could say heuristically it's a change in position, and that's a change in the rate of change of position. Okay, so it's a change in gradient. Okay, so and we're setting these equal to 0. Okay, so we're saying that all of the changes are equal to 0, so we're assuming it's sitting in some equilibrium position. Okay, so now we're interested in these values qi. Okay, so the actual values for qi are, we're going to have, well, I is equal to 1, so q1 is just going to be our theta 1, and our q2 is equal to our theta 2. Okay, so we're going to end up with two equations, so I'll just get this in here before we go on to the next page. So we're going to have the Euler-Lagrange in 2 dimensions, so we're going to have d by dt of partial L by partial Q 1 dot minus partial L by partial Q1. So that's going to be one of them, and the other one is going to be d by dt over partial L by partial Q2 dot minus partial L by partial Q2 equals 0. So these are the two Euler-Lagrange equations that we're going to use in order to derive the differential equation. Okay, so I'll pop on to the next page here,